committee. On behalf of our SVAN coordinator, Claudia Sagastizabal, I would like to welcome you all to this mini course on scenario generation and sampling methods. This is a mini course by professors Güzin, Bayraksan, and Tito, Homem-de-Mello. Before passing the stage to Tito, I would like to give you some information on our thematic program. It's going to be just a short introduction. This mini course is the first one in this thematic program. Is a thematic program on stochastic variational analysis. IMPA's thematic programs consist of several activities along 3 or 4 months for graduate students and researchers work on a specific topic, but interested to significant portion of the community. So this is the case of the stochastic variational analysis thematic program. So which is a relatively specific topic covering stochastic optimization, stochastic systems, and also stochastic variational inequalities, but having a wide range of applications in finance, economy, and engineering. The goal of this thematic program is to bring to the attention to Brazilian mathematicians, and especially Brazilian mathematicians, the importance of a stochastic program. As Claudia mentioned in the opening event of this program, Brazil has a long tradition stochastic program among the engineers, but this is not the case among the Brazilian mathematicians. Thus, the aim is to wake the interest of mathematicians, graduate students, and professors to this very interesting and challenging field that is stochastic optimization, and more widely is stochastic variational analysis. So this thematic program consists of several activities along 3 months. It is organized by Claudia Sagastizabal, Alfredo Güzin, Juan Pablo Luna, Hasna Zidani, and myself. Well, the first event of this thematic program was the workshop on analysis and applications of stochastic systems. So it happened here, took place here at the IMPA, the end of March. So the event brought many researchers around the world, many specialists. It was a very interesting workshop. If you lost it, you still have a chance to watch the talks, because the talks are available on IMPA's web page on YouTube, so you can watch the talks through YouTube. Another event is the basic course on stochastic program, which is a graduate course that has been broadcast throughout Brazil and South America. We have students from Chile, from Argentina, from several universities in Brazil. This course has been given by Claudia Sagastizabal, Juan Pablo Luna, and myself. And in these 2 months, now May and June, we are going to start with our mini courses. So the first one is the scenario generation and sampling methods by Güzin and Tito. Next week, we are going to have 2 mini courses. One is stochastic convex optimization methods in machine learning. This course by Mark Smith from University of British Columbia. The same week, also next week, another mini course, Equilibrium, Royalty and Uncertainty by Professor Roberto Cominetti from University Adolfo Ibáñez in Chile. In June, we are going to have a mini course, Stochastic Rational Inequalities by Professor Roger Wetz from University of California. Then the last mini course will be Stochastic Optimal Control by Professor Hasna Zidani. So this is the calendar of this month, the activities of the thematic program. So, the basic course on stochastic optimization happens on Tuesday and Thursdays. So today we are going to start with this mini course. Next week, here's the schedule for the 2 mini courses and also the basic course on stochastic optimization. So people interested in attending all the activities can attend all the activities because we don't have an intersection in the schedules. For the month of June, the 2 mini course will happen in the week before the ICSP. We still have a special conference in the same week in June 22nd. The title is Stochastic Rational Inequalities in Dynamical Framework. It will be by Professor Rockefeller from Washington University. And then we are going to have the last event, that is the ICSP, it's the International Conference on Stochastic Program. Professor Tito and Professor Alejandro Jofre are the chairs of this conference. This is a conference co-organized from Brazil and Chile. Yeah, you are the chairs. And okay. Yeah, sorry. Yeah, that's a good point. Thank you. And well, in the organizing committee there is also Claudia, Michael Solodov, Alfredo Yusin, Jorge Zubelli, Juan Pablo Luna, and myself. We are going to have many important researchers giving talks, mini courses, plenaries, semi-plenaries. For example, Güzin will be one semi-plenarist in this conference. If you do more information, you can access this web page. And well, I want to give one last information because we need to report to funding agencies. So I would like you to sign an attendance list. So I have here names, the people that have registered to this mini course. I will pass this list among you. I would like you to sign, please. If your name is not here, please write it down in at the bottom of the paper sheet. And if you haven't registered yet, please do it as soon as possible because, as I said, this is going to be important for us when we're reporting to our funding agencies. Well, so here we go. It's my pleasure to introduce the two speakers, the two professors of this mini course. Professor Güzin Bayraksan and Professor Tito Homem-de-Mello. Tito will start and Güzin will continue. I think there is on Wednesday. Okay, on Wednesday. Güzin is an associate professor from Ohio State University in the United States. Tito Homem-de-Mello is an associate professor from University Adolfo Ibáñez in Chile. So they are very, very well-known research in this field of stochastic program, working on scenario generation, working on sampling methods, multi-stochastic optimization, and risk-averse optimization. So the theme, the topics that will be addressed in this mini course, some of them are methods for generating scenarios, overview of properties of such methods, and application to these methods in areas of energy and finance. On behalf of the organizing committee, I would like to thank you, Professor Tito and Professor Güzin, for accepting to give this mini course that I'm sure will be really interesting. So I now pass the word to Professor Tito Homem-de-Mello. I think it's
on, right? Yes. Okay. Well, thank you, Wellington, for the nice introduction. Well, it's a pleasure for me to be here teaching this course. I really appreciate the invitation. I think this is a wonderful program. This is one program that is putting together talks in different mini courses and talks in different areas like stochastic programming, stochastic variation inequalities. I think it would be extremely important, I mean, to disseminate more this area, particularly in Brazil. Like Wellington said, it is being stochastic programming here has been mostly developed in the energy sector, among engineers, but there's a lot more. There's many other fields that can benefit from these tools. So we hope that you guys are taking the course now, and with these mini courses, that this can can open up to other possibilities of application as well. So that's it. Just to get an idea here among those of you who are standing or sitting here, which of you are students of IMPA? Just to, okay. And the rest are researchers from different places. Yes, yeah, just to, okay. So I will assume also that you guys know the basics of stochastic programming. I know that the ones that the students are taking the course, right, with Wellington, Claudia, and Juan Pablo. So the point here, right, the goal of this course is not to talk about stochastic optimization in general, to teach you algorithms. It's not, okay? That you're seeing elsewhere. What we'll talk about here is particularly the issue of scenario generation and sample methods, which we will see soon, that is very much related to, it's one particular way of doing scenario generation, for stochastic optimization problems. Okay, so we will be concentrating in many different aspects of that, but we will be not talking about algorithms for solving the problems. That is by you see that elsewhere. Okay, so just to make it clear up front what this is, what the course is, and what it's not about. Okay, all right. So let's see. Does this one work? So just
yes.
Okay. Well, Wellington had already introduced this, so no need to introduce again. My colleague Güzin Bayraksan, she'll be here on Wednesday, so which means that the way we structure the mini course, we have 8 sessions. So I'll give the first 2. So you have to bear with me the whole day today, sorry, right? So then on Wednesday, she will be here. So she will actually teach 3 sessions on Wednesday. Okay, and then on Friday I come back, okay, and then the last session, I think she teaches the very last session in the course. So we divided like half each, okay. So that's more or less the idea. So as I mentioned, she is at Wellington, also said, she's at the Ohio State University, and I am with the Universidad Adolfo Ibáñez in Santiago. Okay, so let's start with something very simple, which I'm sure you have seen, but just kind of to motivate, okay, the course. So, of course, imagine that you have a linear program. Many problems can be formulated, right, linear programs. But imagine there is some uncertainty, right, in the coefficients. Okay. Oh, by the way, before I start here, maybe I should mention about these slides. Since we'll be doing mostly slides, I know it's hard to follow. I can make the slides available later, right? So no problem. Okay, so you don't have to copy, because it will be impossible to copy everything, right? So I have no problem making it available. So just to let you know up front. Okay, so back to our problem here, right? So imagine that you have some uncertainty, right, in A and C, for example, right? So, for example, this constraint could be, well, the total energy production must satisfy demand, right? And the problem, of course, demand is uncertain, right? So typically, this would be on the right side, but also it could come from the matrix A, right? So the actual amount produced for each energy source could be also random, right? And that's very much the case, especially with the renewable energies nowadays, that you have uncertainty also in the production, okay? Well, so then what to do, right? So there are, of course, many ways one can approach. This is kind of a modeling issue, right? How do we model these problems? So, of course, one of the possibilities is just to say, okay, I'm going to impose that this has to hold regardless of the outcome, right, of these random variables. This constraint has to hold, right? That's one way of doing it, right? That's probably too strict, right? Because that means that you're going to be looking at every possible, even the most unlikely realization. You want to make sure that the constraint is satisfied, right? That's probably imposing too much. That is typically too conservative. So normally what people, one alternative is to say, okay, let's not be so strict, right? And say that I want to impose that this holds regardless of outcome, but only with some probability, right? Let's fix some threshold and, okay, with 95% probability, this is satisfied, okay? Or one can think of doing some kind of expected constraint violation. Say, okay, let's say that I'm going to penalize here the amount of violation, right? And then, well, but this is going to be a random quantity, so I'm going to take the expected violation and put a penalty, mu, right? And now my objective function becomes something like this, right? I minimize the function plus the expected penalty, right, for some penalty that I fix. That's another way of doing it, right? So that's, as I said, those are modeling choices that one makes, right? When you build your model, you have to make these choices, okay? Well, I mean, I'm sure you guys have seen similar things in your course, right, in stochastic optimization. But the difficulty here, of course, is how to solve, right, this formulation. So each of them has different types of complication, right? But here, so here's the thing, right? Even before we think of methods to solve these problems, we actually have to deal with something that's more basic than that, right? Which is, well, how do I compute these quantities? Even computing them is not so simple, right? If you think about it, right? It's, how do I compute this probability, right? I may know the distribution of A, may know the distribution of C, right? But how do we calculate this probability? Right? If you actually write this down, right? What is it going to be? This is essentially an integral, right? I know the distribution. Imagine we know the distribution of this random variable. But this is like this is a convolution, right? It's a sum of random variables, right? So you're taking the sum of the random variables. By calculation, the probability that the sum of the random variables is bigger than the right-hand side. But the sum of random variables can be as complicated as it gets, right? So it could be, imagine, I don't know, each of them, if they're normally distributed, of course, sum of normals is normal. But imagine they have some other distribution, some exponential or, I don't know, gamma, whatever, right? But then the sum is much more harder to handle. So calculating this probabilities explicitly or analytically is very difficult, okay? Same thing with expectation, right? Even a simple expression like this, right? Because it involves a max, it's not so easy to calculate, right? This type of expectation. There's a breakpoint here. You have to partition the integral in two parts, right? It's complicated. Imagine, like, especially if it's one dimension, of course, it's much easier. But think that this is also typically very high dimensional, right? That's what makes these calculations difficult. So, by the way, you guys can interrupt at any point with questions, okay? Feel free. The idea is that we make this interactive, okay? So feel free to interrupt me at any time when you with questions. So this is very hard to do, right? So we need to approximate, right? This quantity is something we can actually compute, right? So I don't know how to calculate these probabilities. We cannot calculate this exactly. We need to approximate. That's the point, right? Then once we have the approximation, then we can start thinking about solving these problems, okay? But first of all, we have to deal with the approximation. Okay, is that clear so far? Okay. Okay, so just to give an example, right? So where these issues arise. So let's say even think of a case with no optimization, right? Just a very simple estimation problem. So imagine that you have a vector, right? Have m random variables, okay? Let's call it x1 to xm. And we want to calculate the function, a function of a real valued function of these random variables. Okay, so arbitrary function, right? This function maps the m-dimensional random vectors to the real numbers, okay? In fact, let's think of an even more concrete case, right? Imagine that we want to calculate the completion time of a project. right? So imagine that I have a project that has 3 components, okay? So they have I have activity 1, and then another activity is given by 2 and 5, and another activity is given by 3, 4, and 5, okay? So to complete the project, I need to have everything done, right? So I need to complete all 3 components, right? So those are the activities. So this is the first component, the second component, and the third component. I need to have all components finished before to say, okay, the project is done, okay? So imagine now that you want to estimate the completion time of this project. Right now, each activity has a random time. It's random, right? Because there's many sources of variation for each activity. So each of them is random, okay? So of course the completion time is random. That's a problem that happens in practice all the time, right? I mean, this is project management. It does exactly this type of problem, okay? So how do we, what is the completion time here? If it was deterministic, what would be the completion time? If there was no randomness. Suppose there is no randomness, right? So that's very simple. Right? So if there was if everything was deterministic, what would be the completion time? I need to finish all 3 of them, right? So I need to finish 1. I need to finish a component 2, which is 2 plus 5. And I need to finish the third one, which is 3 plus 4 plus 5, right? So what is the total completion time? The maximum, right, of all 3, right? So we just take the maximum of x1, x2 plus x5, and x3 plus x4 plus x5. That's it, right? The maximum of those, that's when the whole project finishes. Is that right? So if the times are fixed, right? If there is deterministic, if they're deterministic, you just calculate this max and that's it, right? That's very, very easy to do. But imagine now that the times are random, right? Now the times are random, the completion time of the project is random, and we want expected completion time. For example, right? Let's say I want to calculate the average completion time. So now what do we have to do, right? We have to calculate the expected value of this expression. And that's not particularly easy to do, right? Again, in some cases, maybe if you have particular types of distributions, you can apply, do integral by parts and so on. But in general, this is going to be hard, right, for an arbitrary. And these random variables could have different distributions, right? One of them could be normally distributed, the other could be exponentially distributed. It could be anything, right? So if you try to calculate this, explicitly, good luck, okay? That's going to be hard. So how to do that, right? So we want to estimate simply just that, right? Just take this expected value. So what else can we do? Right? If you think about what else can we do here, right? We want to estimate this max, right? So one way is to say, okay, suppose that I know that each variable takes 3 possibilities only, right? I have three possible values for each random variable, right? 10, 20, and 30, right? Whatever. And with certain probability, right? So 3 scenarios, right? For 3 possible outcomes for each random variable, okay? So if I knew that each of them take 3 possible values, let's assume for simplicity that they are all independent of each other, okay? So they are, probabilistically independent. So if I knew, right, if I know the distribution of each one, that's 3 points each, what do we have to do? Well, that calculation simply boils down to this, right? Now we have to do G, right, of each value, right? And then I have to sum over all possibilities, right, from K 1 to R. Like here, for simplicity, we are assuming, right, we are calling them xk1 to xkr, right? So we have to take this, what's the expected value, right? It's the sum of all possible values multiplied by the probability of each possible value, right? So we end up, now, this calculation, this is exact. There's no approximation here, right? But this is an exact calculation. It's just equal to the sum of all these terms multiplied by the probabilities. Does everybody agree? Right? Well, but how many terms are in this sum? Right? So if you have, imagine R is 3, right? Let's take even a simple case where R is only 3 values for each random variable. How many terms do we have in this whole sum? Each of them takes 3 values, right? So how many variables we have? M, right? So what's the total number of outcomes that we have here? 3 to the power m, right? So we can see that this just blows up very quickly, right? We don't even take, I mean, even with 3 points, imagine that you have an m equal to 10 or 20. There's no way you can enumerate everything, right? So for example, if you have, now imagine each random variable can take 10 values. So just in that completion time example, we have 10 to the power 5, we have the 100,000 possible outcomes. You can say, okay, 100,000 is doable, right? Put this in MATLAB, you can easily calculate. Yeah, but now imagine you have a project like this, right? The same principle, right? It's the same type of problem, right? It's a completion time, right? Where you have, but now we have many more activities going on, right? And different types of components. So calculating the maximum over all of this, that's completely impractical to do, by enumeration. There's no way, right? You can do that by enumeration. So that's why you need to approximate, right? It's impractical to get the exact value. And of course, things get even worse if the distributions are continuous, right? Then it's virtually impossible to do, right? If you have continuous distributions, then there is no way, right? Just trying to calculate that quantity that even just taking the maximum here, there's no way. Okay, so there is a need for to approximate the problem using a set of scenarios, hopefully not too large, right? So I want to approximate, like in this case, I want to approximate this sum. Let's say, we'll say, okay, we cannot really enumerate every possible term here because there will be too many, just to calculate, even though it's just a sum, right, and a product, even though it's a simple calculation, but just the number of terms here will be so big, we cannot do it, right? So we need to approximate that somehow. So one way to approximate is to select a finite number of scenarios and say, okay, well, we're going to approximate this sum only with a finite number of scenarios and hopefully not too large, right? Because so we can still do some kind of calculation. But then, of course, the issue is, well, how do we select that, right? So if you're going to approximate this whole sum, which could be, it could be an integral, right? It could be, in case of the continuous case, it's not even a sum. It's just it's like a multidimensional integral. Well, you want to approximate that, well, with a finite number of scenarios, well, how do we select that? How do we pick, right? And then, well, and what kind of guarantees can we have, right? Once you select a certain number of scenarios, what kind of guarantees can be given, right? There will be an approximation error, for sure, right? But what kind of guarantees can be given? So what we're going to see, this is kind of a way of introducing the course, right? Is that essentially we're going to look at 2 classes of approaches for these approximations. One will be based on sampling methods, which is to say, okay, I'm going to approximate this sum with, I'm going to take samples of these random variables and approximate through sampling, okay? Or we can see there will be a different type of methods that will be deterministic. Say, okay, we're going to approximate this. I'm going to choose my points, my outcomes, my representative outcomes, right, somehow. So I can approximate all these integrals and all these sums with these points that I carefully chose. That's kind of the idea, okay? Of course, we're going to see all this in the context of optimization, right? So I just introduced the problem here for, as an estimation problem, but the goal here is to see how this plays a role in the context of the optimization problem, the stochastic optimization problem. So what's the effect of using these approximations in the context of optimization? Okay, so that's where we want to get. So each class of methods, right, we will require this, we will see the tools here for methods that are based on sampling and methods that are deterministic. The tools are completely different. Okay, so we're going to take a look at those tools in both cases and see how we can answer these questions, right, of selecting the set of scenarios to approximate these functions, and what can we say about the guarantees. Okay? Is it clear so far? Questions? No? Okay. So let's still focus on the estimation problem for the moment, okay? Just to understand a little bit of these two classes of techniques, right? So we said we have sampling techniques and deterministic techniques. So let's first see how the sampling techniques would work in this context, right? So suppose we have, remember we wanted to solve this problem here, right? Where we have simply calculate the expected value of a function of a random vector. Okay, that's what we want to do. So one way of doing it, right, is to say, okay, we're going to take samples of these random variables, right? So I take, for example, in the completion time example, we would take one sample from each x, right, from each activity, okay? So let's call it xj, right? So x superscript j will be a vector, which is one, so this is one sample. If they are independent, if the random variable is independent, to do this, you just have to draw one sample from each random variable. That's easy, right? You just draw one sample from each one. If they are correlated, it's a bit more complicated because now when you take the sample, you need to take the correlations into account. But still, there are methods for that, okay? So we can always take a sample from the whole vector, right? So we remember x is a random vector, so this is just one sample of that vector, okay? All right. So imagine now that we draw n independent and identically distributed samples. So here is important that the fact they are independent and identically distributed, right? So there is no, so they all all the samples come from the same distribution and they are independent of each other. As you'll see later, in fact, what Güzin is going to talk about on Wednesday is there are ways you can do this when you drop the independence assumption, for example. And one sometimes can do better by doing sampling without the assumption of independence. But I'll let her talk about that, right? So for now, let's assume this is just a standard sampling, right? That we see, any software, MATLAB, and even Excel has sampling, right? So you imagine that you draw these samples, right? And then what do we do, right? So if you want to estimate that quantity, right? So remember we wanted to estimate, right? We have the expected value of g of x, right? This is what we want to estimate, right? And imagine now that we can draw samples, right? We have samples x1 to xm, right? We have n samples. Oh, n, sorry. This will be capital N. M is the dimension of x, right? So each of these is a vector, right? So now if you can draw the samples, the problem is easier, right? Because now all we have to do is to calculate the average of these functions, right? We just calculate the average and say, okay, that's called g hat n. This is an approximation of my e. My expected value, right? Well, what ensures that this is a good, what kind of result ensures that this is a good approximation for that? How do we know? How do we know that Gn approximates EGX? How do we know that? Huh?
Law of larger numbers.
This is just a strong law of larger numbers, right? Strong law of larger numbers essentially says that, well, when you take averages, right, if you have some very mild assumptions, right, like finite expectation and so on, under very mild assumptions, when you take the average, right, this converges, right? The strong law of large numbers says that as n goes to infinity, right, the limit, in the limit, well, this is a random variable, of course, right? This is a random variable because it's an average of random quantities, so this is a random variable, right? So, but this is saying that, okay, with probability 1, so no matter which experiment you do, think of this as being an experiment, right? No matter which experiment you do, once you take the averages, this is going to converge to the expected value, right? This is like flipping a coin 1,000 times, right? You flip a coin 1,000 times and you take the average, of course, this is going to get closer and closer to 1/2. Let's say we have 1 is tails and 0 is heads, right? You take the average, it's going to converge to 1/2, right? So essentially, that's what this is saying, right? Ultimately, we will converge. No matter which experiment you do, if you do long enough, this gets closer and closer to the expected value, right? So then this is saying, okay, so because I have this strong law of large numbers, I know that G is a good approximation. I can use an approximation of the true value that I want to calculate, right? To estimate. So this is fine, right? So we are essentially relying on the strong law of large numbers, okay? Well, but then of course one can say, well, that's good, but the problem is this depends on the sample, right? Like I said, sometimes if you think of a sample as being an experiment, right? Sometimes you can do an experiment and, after 10 draws, it already converges to the expected value. Sometimes it can converge much longer, right? So it varies, right? So if you fix, for a fixed n, anything could happen in principle, right? For a fixed n, it could have, in fact, for example, here's the result of 200 runs, right? So I just did this for the completion time problem that we discussed before, right? So I did 200 experiments with n equal to 50, right? So this is what we see, right? So I forgot what was the exact time there. I think was something around like 24 and 25, okay? So we can see that this is most of the values are concentrated here, but sometimes you can have values that are much lower and sometimes they're much higher, right? So there is an error because, well, that's the randomness of the sampling, right? So of course we have a tool for this, right? We know by from statistics that there is these estimators here actually have a normal distribution approximately, right? Asymptotically they have normal distribution. So then, essentially that's the central limit theorem, right? That tells us that, okay, if I know that on average this is what we wanted, right? The expected value of the estimator is my true quantity, right? And we also know that the variance of this estimator is just the variance of the original quantity divided by n, right? So this variance, of course, the variance of the estimator goes to 0 as n grows, right? So the central limit theorem essentially tells us that, okay, I know that for n sufficiently large, the square root of n, if I take my estimator minus the true quantity divided by sigma, which was sigma is the variance, the standard deviation of the original variable, we know that this is going to be asymptotically 0, 1, right? That's what what we learn, that's basic statistics here, right? We know there's a convergence to normal 0, 1. So from that, we can calculate confidence intervals, right? We can say, yeah, okay, so then the probability that my true value is between these bounds, right? The Gn minus 196, which is that, right? That's just the inverse of the normal distribution, sigma over the square root of n, right? So this is, I take this interval here. So this probability is going to be 95%, right? Which means, well, what is this saying? That out of 100 experiments, right, on average, 95 of those will be in the interval given by that expression, right? So here's already something important to pay attention. Sometimes, right, when I teach this to students, oftentimes people make the mistake, right, that they do an experiment and they get a confidence interval, right? Once they do that calculation, they get a confidence interval, say, 10 to 20, right? And then they say, okay, this is my confidence interval, so that means there's a 95% probability that the true value is going to be in this interval, right? So what's the problem with that interpretation? If you say, okay, there's a 95% probability that true value is between 10 and 20, So what's the problem with this statement here?
Fact is 95% of the cases, the event will appear in that interval. Is that?
Well, let's think about it. Let's just think of this statement itself, right? What is the problem with this, making such a statement? "95% probability that the true value is between 10 and 20. 10 and 20, right? We are assuming this is what came out of that calculation, right? So what is the problem with this statement? Huh? Felipe? Huh? Exactly. The true value is a number. I just don't know what that number is, but it is a number, right? Maybe the true value is, I don't know, 15.7, right? So we cannot say there is a certain probability that the true value is between this interval, because either the true value is here or it's not. There is no probability, right? This is just a number. Either my number is between 10 and 20 or it's not. There's no, you cannot say about there's a probability here. There's nothing random about that, right? So this is important because it's a confusion that people often make when they interpret confidence intervals, right? So this interpretation is wrong because, no, either it is or it's not. The probability is 100% or 0%, right? So what the way to interpret is, right, what Wellington was saying, which is to say, okay, what we can say is that on average, out of 100 experiments, if I do 100 experiments, on average in 95 of those, the interval will be given by this expression, not necessarily those specific numbers, but it will be given by whatever results from my calculation, right? So if I do one experiment, maybe I get 10 and 20. If I do another experiment, maybe I'm gonna get 12 to 24, right? And then I do again, I get another interval from 13 to 17, and so on, right? In fact, if you think about, we could draw here, imagine we do one experiment, right? Like in this case, I get 10 to 20. And then I do another one, I get 12 to 24. I do another one, and then I get something like here, right? From, I don't know, 8 to 16, and so on, right? So what this is saying that, imagine that the true value is here, right? Imagine that this is the true value that I want to calculate, to estimate, right? So essentially this is saying that, well, if I did this 100 times, right? On average, 95 of those the interval would go cover the true value. Sometimes I might be off, right? But most of the time, I am in. My interval covers the true value. So that's what it means to have a 95% confidence, right? To say, well, whatever came out of the experiment, I'm 95% confident in that sense, right? That, you know, there's only a 5% chance that I was unlucky and my interval did not cover the true value. Okay? So that's why we call it a 95% confidence and not a 95% probability, right? So that's important to remember the interpretation of confidence here. Okay, so then of course sigma is usually unknown, right? You don't know the variance, right? You don't even know the mean. How can you possibly know the variance? And normally you're not going to know the true variance, but again, we know that you know, if n is large enough, you can approximate the sigma squared, right, the variance, just by the sample variance, right, which is you take each term, subtract the mean, take square, and divide by n minus 1. Remember here you have to divide to n minus 1, divide by n minus 1 to make sure your estimators are unbiased, right? If you divide by n, which might be more natural, more intuitive, you get a biased estimator, right? So we have to divide by n minus 1 to get an unbiased estimator. Okay, but once you estimate this, then it's easy, right? Then to calculate the confidence interval, you just take the square root of this guy here, plug it, replace sigma by the Sn, and then you have a confidence interval. That's how we get these numbers like that. Okay? So that's how we would do through sampling, right? So that's how we do, how we would estimate the completion time through sampling. So we were able to get a number and an interval, right? That we have, say, 95% confidence that the interval covers the true value. So that gives us a lot of information, right? We were able to get an estimated quantity and a measure of the error, right? So this is good. This is a good way to approximate that unknown quantity. Well, another way, one can also think of deterministic approximation, right? So one possibility is to approximate the distribution of xi, right, with a distribution that has a small number of points. So, well, if you go back to those methods that we learn in calculus, right, like Simpson's rule or trapezoidal rule, all those rules, right, they're essentially ways to approximate integrals, right? For example, the Simpson's rule, now you approximate with a polynomial, like a Legendre polynomial, and then you just evaluate the function at a few points, and then you take you estimate your integral based on the function value at those points that you define, right? That's essentially what these rules are. So we could do one with, say, 3 points, right? Sure, we can approximate an expectation is an integral after all, right? So you can just use those rules to approximate the integrals, say with 3 points. So we know those techniques work well, right? I mean, they are used a lot. But what is the problem here of using these techniques? What's Yes, they're going to work only for low-dimensional problems, right? Because once you go to high dimensions, well, if you need, same issue we saw before, right? Even if you do a 3-point approximation on each dimension, well, if you now have 2 dimensions, you're going to need 9 points. In 3 dimensions, you're going to need 27, right? This is a grid, right? So this blows up very quickly, right, with the dimensions. So this type of approximations are only practical if you have small dimensions, 3, 4 dimensions maybe, but more than that, these deterministic approximations don't work. Okay, at least done this way. This is kind of, you can think of this as a naive way of doing these approximations, okay? Where you're just taking, you just try to approximate each coordinate with 3 points. Again, as we'll see later, and Güzin is going to talk about on Wednesday, there is an entire class of methods. There's a whole community that studies what's called the quasi-Monte Carlo methods, which essentially do, what they do is to say, okay, I want to approximate integrals. There's nothing to do with optimization, right? It's just a problem. I want to approximate these integrals that are high dimensional, and I want to somehow choose my points in the space, in this multidimensional space, to get a good approximation. So there are many, many techniques. As I said, there's like an entire community of people who work on these problems, right? And we are able to use some of that in stochastic optimization, right? So there is some research on that, on using those methods that have been very, very, very well developing in that area with rates of convergence and everything. But Güzin is going to talk more about that on Wednesday. So those we can view those as deterministic approximations as well, but they are smarter methods, right? Smarter than just this naive approximation where you just do each component separately, right? Okay. So of course, the problem here, right? One is, well, it's difficult. We still have 3 to the m terms, right? So there's the dimension issue. And also, it's difficult to assess the quality of the approximation, if you think about it, right? If you take here, one thing that was extremely important was the fact that we could construct these confidence intervals and give a measure, right, of the error, how much error is involved, right, in my estimate. If you do the deterministic approximation, how do we know how far it is, right? That's a problem, okay? So even in these quasi-Monte Carlo methods that I mentioned, they also have that problem. Right? It's very difficult. You can find bounds, but those bounds typically are more qualitative, right? It's just those bounds is just to give you an idea of the order of the rate of convergence, but they are not practical in the sense of getting an actual measure of error. This is extremely hard to do. Okay, so that's one big advantage of sampling methods is the fact that one can get a confidence interval and say, okay, I'm 95% confident that this gives me the right value. Okay, that's something important to remember. Right, so we already mentioned these quadrature rules, right, the Simpsons and so on, but again, they work well only for these low-dimensional problems. Okay, so any questions up to now? Are we okay? Okay, so now we go to optimization, right? So we just, the idea now, so far was just to give you a brief discussion of these estimation problems, right? Even without thinking of optimization, because as I mentioned earlier, before you solve the optimization, you have to think about how to even evaluate the functions, right? So, but now our real interest here is to go back and solve the optimization problems, right? So this is the stereotypical problem we're going to be looking at, right? Throughout the course, as a matter of fact, right? So our problems will be of this form, right? I want to minimize a function, right, of x, and this function is given by the expected value of another function, which depends on x and depends on some random component. Okay, so we can think of this c being some random vector, for example. Okay, so this expected value, right? So for each x, if you calculate the expected value, we get a g of x, and then I want to minimize the function in terms of x. Okay, so I'm sure you guys who are taking the stochastic optimization course, you've seen many problems of this form, right? For example, all two-stage problems, right, can be formulated this way, right? Where g, you can think of g as being the second stage function, right? The recourse function. But many other problems, you can even think of this being a multi-stage problem, right? G being the result of the cost to go, right? From next stage on, right? So, but here we're going to think of this more in a sort of a general context, right? So I want to minimize the expected value of this function, which could be cost, revenue, whatever, okay? And capital X here for us is going to be the set of feasible points. So here is one important comment is that for the moment, okay, we will assume that X is a fixed set, okay, deterministic set. Right? Just think of this given by constraints, so it would be like a polyhedral set or a convex set, typically, right? But deterministic, right? So later, we'll see the case where even the feasible set itself could also incorporate some uncertainty, right? We'll see many cases where this is important to include. But for the moment, let's assume that the feasible set here is just fixed, okay? Deterministic. Okay. So we want to, so that's the problem we want to solve, right? So if g is not a simple function, or if the c is not low, the same issues as before, right? We have to approximate the problem, and because we cannot estimate the g of x exactly, right? We only have approximations for it, right? And as before, we can do either sampling or deterministic approximations, right? But now we have a slightly different question, right, as before. So before we were just saying, okay, what can we say about the quality of the approximation when we were doing the estimation problem, right? That was just a matter of saying, how far are we from the mean, right? We do like the sampling methods, for example. We were just saying, well, how far are we from the mean of the problem? But now, there's an extra step, right? Because once we approximate this problem, let's say we don't have this expectation, we replace it with something else, right? Well, we have to think of what's the effect of that approximation over the optimization problem, not just for each x, but over the overall optimization, right? So that's the main difference between, if you think about it, right, what people study in statistics or in simulation versus what they study in optimization. I talk often to people in these other communities, and almost all the time, this is the main difference between what they do and what we do in optimization, right? The fact that for them, as long as you can only need to say things about a particular point. But now, for us, just having x alone is not enough. We need to know what happens. You're minimizing over x as well. So there's an optimization problem, right, together with that. So it's not just an estimation issue, but it's an estimation issue together with optimization. So what is the effect of approximating this problem in the overall optimization? That's essentially the issue we need to address, right? Do we get something, will the optimal values be close? Will they be far? Or again, can we say anything about rates of convergence? Can we get confidence intervals? No, all sorts of questions, right? But now think in terms of the optimization problem. So that's essentially the issue we want to address. So what is the effect of this approximation? Okay? Is it clear, the question? Okay. Okay, so to illustrate that, okay, so let's think of a very simple problem that we know. The reason I'm putting this very simple problem because we know a problem for which we know the solution, right? So we can easily see the effect of these approximations, right? Rather than putting a complicated problem for which we don't know the true answer, it's easy to see in this case. So the Niels-Vendor problem, this is a classical problem in stochastic optimization, right? That's like the very basic problem, right, one can think of in terms of stochastic optimization. So what is that, right? So the Niels-Vendor buys the papers in the morning for a certain price, and then it sells during the day at price R, right? And then the papers that are not sold, I can sell them back for some salvage value S, right? So typically, of course, the value of R is bigger than C, right? I need to have some profit, right? Otherwise, we won't even be in business. And the salvage value is going to be between C and R, right? So it's something that is worth more than my purchase price, sorry, less than the purchase price, right? Otherwise, I would just keep buying forever, right? And it would make infinite amount of money. No, it's less than the purchase price. And so you can think of S is less than C and C less than R, right? That's the way to be in business here, okay? Okay, so we can think of this as a particular case, right, of the problem we saw earlier, right? So what we want to do here is to minimize this function here. So this is this is our, in fact, here we are maximizing. Sorry, I should have written as a maximization problem, right? So this is minus the cost, right? And this is my revenue here, right? So it's what I sell is, well, the minimum between what I order and the demand, right? I sell for a price R, and this is what the leftover, right? So we get this expression here, but that's the difficult part, right? We get this minimum between X and C. So again, calculating the expected value exactly of this quantity is cumbersome, right? Well, in this particular case, it can be done. I mean there is, because it's one-dimensional, one can come up with an integral. But again, this is just to illustrate a more general idea, okay? So if you were to do this by sampling, that would be very easy to do, right? We just take a sample of the distribution of demand, right? And solve the problem and approximate the problem. Well, we know the solution of the Niels-Vendor, right? So we're going to draw a sample, right? And I'm going to approximate G with this, right? So it's just an average of the cost function, right? And then we see what happens, right? But here's one problem, right, that arises. That's the issue that I was mentioning, the optimization versus the estimation, right? We can certainly do this for all x's, right? For each fixed x, I can certainly approximate this function, right? I just look at that expression, right? Plug in multiple values, right? And then just take the average of this quantity. But if you plot a graph, this is what you're going to get, most likely, right? So for each x, I have an estimator, right? I fix x. I get an estimator. So the blue here the graph is a little bit weak, but you can think that this curve here is the actual function, okay? Is the g, the true function g, and the dashed lines here are the value. It's connecting the value that I estimated for each x, okay? So when I did x equal to 2, I got this estimator minus 1.2. Then when I did 2.5, I got this estimator here. Here for 3, I get this estimate, and so on, right? So if I want to optimize this function using the blue function, not a good idea, right? I mean, no one will possibly want to optimize this function here, right? That's awful. Right? It's completely out of question, right? That's all these ups and downs, there's no optimization method that will solve this efficiently. Right? So, well, what is the problem here? What is causing this? Or how can we fix this? Any ideas? How can a simple fix? Can we do a simple fix to avoid the problem of ups and downs? What do you think? Huh?
Using always the same sample, varying x.
Yeah, exactly. If the problem here is that we are taking a new sample for each x, right? So that's what's causing this up and down effect, right? Because for each x, I have a completely different set of samples. So yeah, there is no reason why the estimated 2.1 is anything close to the estimated 2.2, because they're completely different samples, right? We know that they will be relatively close to the true value, right, because of central limit theorem and so on. But the 2.1 and the 2.2 could be very far apart, right? And the 2.3 could be, again, far apart, right? So that's why you have this up and down effect. So a good idea is to say, well, why not use the same sample for all points, right? So instead of, you can think of this, instead of estimating the g of x, I'm estimating actually the whole function at once, right? So that's exactly what's called the sample average approximation approach, right? So this is a technique that the methodology exists has been proposed a long time ago. In fact, came from people in statistics back in the 50s or 60s. But it became more popular under this name from the year 2001, to be precise. Okay, there was a paper this term was coined, and it kind of the name caught on, and now people call it the sample average approximation method, okay? So that's essentially the idea. So you say, okay, we're gonna use the same sample for all x's, right? So then what happens? Now, if you use exactly the same sample, right? So now it's like we're approximating the whole function together. So in this case, look what we get, right? So once we use the same sample, so we can see that here's still the same blue function, or red function, right? But look at what happens to the blue one now, right? That's much closer, right? Because again, we are using the same sample, so we are just replacing this guy, right? We are fixing a sample and calculating this using the same functions for all x. So of course, now the value in 2.1 will be very much related to the value at 2.2, related to 2.3, right? They'll be very close to each other because they are essentially calculated with the same samples. So this is a key idea. So it's very important to understand this because that's the key idea behind this type of approach, right? That we are not taking one sample for each one, we're fixing the sample and approximating the whole function together. Okay? So that is the main idea. In fact, you can plot this in MATLAB very easily, right? Just draw a collection of random numbers and then calculate this, right, for each x, do this calculation, and plot. You can easily see that you get something that is very close, right? Or at least it's more, it could be far, but even if it's far, but at least it has the same shape, right? It's not going to be anything like this, right? Because here we have different values for each point. Yes?
Is there any reason why you have large variability when x increases?
Here? This is because of the particular structure of the problem, right? Because the costs of this is the Nussbender function, right? So when you order 0, for example, right? If you order 0, there's only one thing that your revenue is fixed, right? Regardless of the demand, your revenue is 0, right? Think about. So here, in fact, there is 0 variability because it doesn't matter how I'm sampling. My revenue is deterministic, right? It's always 0. So as I increase my order quantity, that's where demand starts having more of a role, right? So here, and that's the effect that you just noticed, right? So I have more variability here because those are the values where demand matters more, right? So here, the high x, and x equal to 5, there's a good chance that I lose money, right? And a good chance that I earn money. So I depend more and more on the demand. Okay? But for low values of x, there is almost no variability. Only here it starts really mattering. Okay? But that's just because of the way this particular problem is, of course. Okay? Okay. And we see the same thing here, right? So it's 0. They are the same value, and then they start being a little farther apart. In this case, it's interesting that they actually go back together here. Again, but that's the consequence of using the same stream of random numbers. Okay, so we see that the approximation is close to the real function, right? There is no, at least visually here, you can say, well, that seems a good way to approximate, right, the true function. But so what is this suggesting, right? Is this suggesting that we just replace the original problem with this problem here, right? So, since we can approximate now the whole function, so why not simply replace the original function by this one, right? Instead of working with the red function here, we work with the blue one, right? So visually, it seems sensible thing to do, right? We are changing a function by another function that is very close, right? So we just minimize. And now this one is just the deterministic problem, right? Because the sample is fixed, right? So I can apply any of the methods that, right, that any deterministic optimization algorithm should do it, right? Or for example, if the original problem was a 3-stage problem, right? You can think of this as being now a 3-stage problem with a fixed number of scenarios, right? So all the decomposition methods, the L-shaped methods and so on that you have learned could be applied here, right? Because you can think of this now as just a problem with fixed number of scenarios. That's it, right? So that becomes very simple to solve, right? Once the sample is fixed. But of course, questions that arise, right? First, does that always work for any function? Do we need? Are there any restrictions on the functions that to make this work? Or what's a good sample size? I didn't tell you what was the sample size I used, right, to get this one, and I'm not going to tell you, right? But what's a good sample size, right? That is the question. Should I use 10, 50, 100,000? How many samples do we need, right, to get a good approximation? And what can be said about the quality of the solution, right? So what can we say once we solve this problem? All we get is an approximating solution and an approximating value, right? Because this is not the true problem. It's only an estimate, an approximation of the true problem. So all we get here is we have some candidate solution and some candidate optimal value. But what can we say about the quality of these estimators, right? Same issue that we had for estimation, but now in terms of optimization, right? So I can think of the solution of this problem as an estimator of the true solution and the optimal value of this problem as an estimator of the true optimal value, right? Those are statistical estimators, but so what can we say? So that's what we're going to be concentrating for the next few minutes. We have 2, 3, right?
3.5.
Yes. Sure. I thought it was 2, 3, and then we come back at.
Then we come back.
Oh yeah. No, there will be another session later, right?
Okay.
There are 2 sessions today. I just want to give a break at the right time.
Okay, no.
Okay. Okay. So at 3 we will have a break. So let's first see what happens as the sample size goes to infinity, right? So let's do some kind of asymptotic analysis, okay? So what happens as the sample size goes to infinity? Similar to what we did in the estimation case, okay? Later we do, then what Güzin is going to do one way is they say, okay, she's going to talk about what can we say about finite n, right? Given that you actually cannot take n going to infinity, right? You have to work with a finite n. What can we say once you have n fixed, okay? But now we want to first make sure that before talking about finite n, we have at least to see if this makes sense to do this approximation, right? So if I take an n going to infinity, do I converge to the right values? So if you don't have that, then we shouldn't even start discussing the problem, right? But so let's at least see if things work well when n goes to infinity, right? So Okay, so first that's important to understand what this means, right? So what is that? So imagine that we draw a sample of infinite size, okay? Call it C1, C2, and so on, right? Imagine you have an infinite sample, right? So we're going to call that a sample path, right? So this is a sample path of this process here, right? You can think of this as being a process where you draw one sample, another sample, another sample. You can think of each realization of this is a sample path, right, of a stochastic process. Okay, now for each n, right, we're going to construct the approximation, right, of the function. Remember, we are now approximating the whole function, right, because we are using the same random numbers. So imagine that I take the first n terms, right, of this sample up to the first n, and I average them, and that gives me an approximation. Let's call it Gn. Okay? So we are doing this with the first n terms, right, and solving this. Solving the problem, the approximation problem with the first n samples, right? So the type of statements that we're going to be making will be related to what happens to this as n goes to infinity, right? So once I am on a specific sample path, but I keep adding more and more terms, okay? So it's simple. That's what the type of, that will be our analysis here, right? So we take n larger and larger. The sample path is fixed, right? We are fixing one sample path, right? One sample of this process. And then I say, okay, what happens as I grow n to infinity? I'm taking more and more terms along this particular sample path, right? That's the idea. So let's just to set up the notation here, right? So let's call it xn. X hat n will be the optimal solution of the approximating problem. Right? This is our problem we're calling SPN, right? So that's our approximating problem. So we're going to call x hat n will be some optimal solution, an arbitrary optimal solution. Sn for us will be the set of optimal solutions of that problem, okay? And nu n will be the optimal value of that problem, okay? So now we compare this to the corresponding values for the true problem, right? So the true problem, let's call it x star. That would be the true optimal solution. Or S star more generally, like maybe the original problem has multiple solutions. So we take S star is the set of optimal solutions. And nu star is the true optimal value. So those are the quantities that we don't know, we would like to know, right? What's the optimal solution, what's the optimal value? But we only have access to these ones, okay? So the question then we want to address now is, okay, as the sample size goes to infinity, okay, do I have convergence, right? Does xn converge to some x star? Or do the set of optimal solutions converge to the true set of optimal solutions? Does the optimal value converge? That's what we want to address now. That clear, right? Notice that this, right, this is the point. This is a set, right? So when you say take here, we talk about convergence of sets, right? But maybe we can say something about that, okay? And this is just the optimal value, right? But so is there convergence, right? Like I said, if we don't have this, we shouldn't even start, right, discussing these methods because there's no hope, right? If there's no convergence, nothing we can do. So, as we'll see, of course, under some conditions this will be true, right? But not see under which conditions. That's the key, right? Okay, so again, let's illustrate these properties with the Niels-Vendor problem. Okay, so we know. So let's study separately. Okay, the case as you see, it's a different behavior when the random variable has a continuous distribution versus when it has a discrete distribution. Okay, we'll see in a second. The behavior is very different. So it's important to understand why it's different and what can we say in either case. Okay? Okay, suppose we're still in the context of the Niels-Vendor problem here, right? Just to keep it simple, just in the context of the Niels-Vendor problem, and we're assuming that the demand, right, of in the Niels-Vendor problem, right? I have a demand with exponential with mean equal to 10. Okay? That is the true distribution here. Okay? Demand equal to 10. So this is my true. The red function is always the true one. Okay? So what we are plotting here is the approximations for various values of n, right? So the dashed line here is the function that we get with n equal to 10 only. You can see it's a very poor approximation, right? It's this function here. The dotted one is the when n is equal to 30, right? Again, this is one sample path only, right? Just one sample path. Different n's, right? So which means what? That the difference between the n equal to 30 to n equal to 10 is that we added 20 more terms, right? So we took the one with equal to 10, added 20 more to get the one equal to 30, right? And likewise, right, now to get the 90, we added 60 more terms, right? 60 more samples and get this dashed and dotted one, which is, let's see here. Where is this one? I think it's this one here. Yeah, right? That's the one, the n equal 90. And with n equal to 70, right, we just like multiply by 3 every time just to see the effect of how it grows, right? When n equal to 70, you get that, I'm sure you cannot see, but here the dots are here, okay? Those are the dots, okay? So as expected, the higher the n is, the better we approximate the function, right? We sort of expected that. But the question is, what can we say about the optimal values, right? And the optimal solutions. So if you think about this point, this function here, right? If you minimize this function, the minimum is probably around here, right? That's the minimum. Or if you solve this one, the minimum is here, and so on, right? So what can we say about these values, okay? So here is a table, right? Since it's hard to see on the graph, but here's a table, right? So this is, I'm listing here the solution in each case, right, for each n. And infinity here corresponds to the true problem, right? In this case, again, it's the Nussbender problem, is we can solve it analytically, right? So we can calculate exactly the solution. So here's what we get, right? So in the case of n equal to 10, we solve the problem, we got 146. When you solve it for 30, you got 144, and so on, right? With, this is the optimal value, right? So what we see on this axis is a minus 111, 084, 098, and so on, okay? And the true value is minus 107, okay? So what do we see? What do you think we are seeing here? I mean, again, it's hard to say. I mean, this is just one sample path, right? But just taking this sample path as an example, what are we seeing? Right, if you look at the solutions for n equal to 70, it's already pretty close, right? The optimal value, sorry. The optimal solution, maybe, right? We are certainly getting closer and closer, right? Still a bit, we can still have even with 270, we still are 10% off, right? The true value. But still, it's better than with 10, where we had only 1.4, right? So it seems we are perhaps a bit slowly, but going to the right value, right? Both for the solution and the optimal value. And again, if you think geometrically, right? If these functions are getting closer and closer to the true one, right? With n larger and larger, it's intuitive that we should be getting the same value, right? The same solution and the same optimal value, right? So, at least empirically here we are seeing that, but what exactly is ensuring that, right? If you think about in terms of the graph, what's ensuring that we have this convergence? Is there anything about these functions that you can even think of this outside the context of stochastic, right? Just think in terms of convergence of functions. So what kind of convergence do we need here to ensure that? Intuitively, right? If this function is converging to this, what kind of convergence do we need to have to guarantee that the optimal solutions at optimal values converge to the true one? What do you think? Huh? Yeah, it looks like we need some kind of uniform convergence, right? Because if the function converges well, converge very fast, right, at one point, but very slowly elsewhere, right? We could have a situation where, you know, your function could be, I don't know, the minimum is here, right? Your functions converge very fast here, but very slowly here, right? So typically, I mean, to get an example of this, one should even take some sort of a discontinuous function, for example, right? But the point here is, if you don't have the uniform convergence, right, you could have the approximation very good outside, very far from the optimal, but here it could be anything, right? So the problem here is, if you want to get the values and the optimal value and the optimal solution, you need some kind of uniformity, right? So that's essentially the tool we're going to need here, that these functions converge uniformly. So that's the way to, there is a concept we were going to see later. There is a concept that generalizes, you can think of this as a generalization of uniform convergence, which is called epiconvergence, okay? So what is the epiconvergence? Essentially is the following, right? You can think of epiconvergence as the following pictorially, without getting into the mathematical definition, but epiconvergence, you can think of this as the following, right? If I have a function, right? Imagine you have a function here, and we draw the epigraph of this function, right? What's the epigraph? Well, everything that is above this, right? Okay? Now think of this as being a set, right? This is a set in R squared, right? Now, if I have another function here, right? Suppose, let's draw it a different color. Suppose I have another function here that is maybe close, but not the same, right? And then I draw the epigraph of this green function, okay? So we can think of what is epiconvergence. So the epiconvergence essentially, in words, is saying that the set, right, which is given by the epigraph, converges to the set, which is the epigraph of the white function, right? So if you have this kind of set convergence, then we say that you have epiconvergence of the functions, okay? So that's a very useful concept if you think about, right? Because you can see why, right? That if you have epiconvergence, it's clearly that the functions are essentially converging uniformly, right? But the epiconvergence is more general than that. So it's a nicer, it's a nice concept because it allows us to generalize, even in cases where perhaps uniform convergence does not hold, but maybe we can ensure epiconvergence, okay? So that's essentially what we'll see that's what we're gonna need, some kind of uniform convergence or epiconvergence as described here. But I want to show something else before that, which is the case of discrete distributions, right? You have a question?
Well, you stop at x equals to 5, but if you go x equals to 1,000, you have a lot of disagreement with this.
Yes, good point.
So and I mean, imposing uniform convergence is too much for
Yeah, and good point. And in fact, what we're going to see soon is that to have this kind of result, we need to restrict ourselves to some compact set, right? So we cannot have this growing, because if you let x to be unbounded here, then it'll be hard to impose, right? But if you stay within a compact set, you can see that at some point, you can ensure the uniform convergence, right? Especially if you have convex functions, in compact sets, at some point we will have uniform convergence, right? But it's a good point, right? One important assumption we will have to make is that, well, we are within a certain compact set, okay? So, okay, so the case of discrete distributions, oops, where were we? So here's what you get, right? In the case of discrete distribution, now the function is a little bit different, right? Because our function now, let's say demand has discrete uniform distribution, right? So it can have only 10 values, each one with probability 0.1, right? To simplify. So this is again the same News-Vendor function, right? So now if you plot the red function, you get this, right? This function here, and then you can see, so if you minimize this function, what do we get, right? You can see that there is a plateau here at the bottom, right? Which means what? That now anything between 2 and 3 is an optimal solution, okay? It doesn't have to be that way. Maybe the solution will be like this, it could be, right? But the important part here is that these functions are now polyhedral, right? Because they are just, the g function is just given by the maximum, right, of a certain function. The capital G, right, the gxc is a polyhedral function, but if the distribution is discrete, we are just summing up polyhedral functions. So the resulting function is polyhedral as well, right? So the true function is polyhedral, and then of course, each approximation is also polyhedral for the same reason, right? So now we are doing approximation of polyhedral functions. So you can think, well, it's still the same context as before, but as you'll see, there is some qualitative difference between these approximations, right? For example, if you, do you observe anything in this graph particular about the approximations in terms of the solutions of the approximations? Look at the blue curves, right? Do you observe anything about the solution? Not the optimal value, but the optimal solution of these problems. Anything in particular you can observe? Think about, right? When you do this one, this is the worst one, right? When equal to 10. What's the optimal value of this guy? 2, right? Now, let's take this one. What's the optimal value of this one? It's hard to say here, but it looks like it's either 2 or 3, right? Now, take the dotted one. What's the optimal value? Optimal solution, sorry, optimal solution. 3, right? That's the minimizer. And, well, the dotted function, again, you cannot see it here, but the dotted function is this one here, okay? It's going here. And if you minimize, you can see the optimal solution is 2, right? So, what do we see, right? So the solution is actually, we only see 2 values of the solutions, right? It's either 2 or 3, right? That is very much different from the previous case, right? In the previous case, we saw anything, right? We had a continuum of values here, right? So the solution could be any number, right? Whereas here, in fact, if you draw a table, if you put this on a table, that's what you get, right? The optimal solution is 2, then 3, and then 2 again with 270, and so on. So it jumps between the 2, right? So this is very particular, right? If you think about that, it's how come, right? It's not like before. Not true for the optimal value, by the way, right? If you look at the optimal value, right, what you get on this axis here, a variety of values, right? The -2, then -250, -167, -135. Well, the true value is -150, turns out. Okay? So we see that this is approaching the true value, but this one, there's no convergence. Right? 2, 3, 3. In fact, we can plot more and more, get larger and larger. You see that the same thing keeps happening, right? You keep jumping between 2 and 3 only. There's no, so xn, strictly speaking, right, if you think in terms of convergence of xn, there is no convergence, right? Do you agree? It's not a sequence that oscillates. Well, there is no convergence. Well, we can say, oh, there's 2 accumulation points and so on, for sure. But xn itself is not converging, unlike the previous case, right? So, and that's no coincidence, right? That will be a consequence of the fact that the true problem has multiple optimal solutions, right? And xn is oscillating. So we're going to see well, how general is this conclusion. So let's take a break now, and then we come back. We talk about more about this asymptotic properties, and then move on to the case also where we have we're going to talk a little bit about the rates of convergence, right? Because this is, for so far you're looking only at the convergence, asymptotic convergence, right? So we're going to talk a little more about the rates of convergence, and then hopefully talk a little bit about the case of when you have some stochastic constraints. Okay? And then there we'll do it for today. So let's take a break. I think we come back in half an hour.
We come back at 3:30.
3:30, yes. Okay, so half an hour break, and